When you reach 1, you wait until you hear 0. Then you go.
Am I supposed to
This person didn't take from me all this.
Are you having no.
Yes. Please, you immediately stop. First, hold on. You stop immediately when you see a fast drop. Alright? No, for you to continue pouring, but the person who is having the stop clock, you immediately see the first drop, you don't want to see how much time they take, okay? Just put that thing, madam, put it to be like this. Because even that time is not calculated, eh? Right? Like this. Okay, referee.
3, 2, 1, 0.
This one already.
Don't make noise, just observe.
What are you trying to say?
Yeah, wait until it.
You are supposed to start. From where? From where?
You're saying the first drop.
He has already stopped.
This person has stopped.
Yeah.
Yeah.
Has stopped.
Yeah.
This one.
Not yet.
Yours is raw or is clay.
You cannot get back your position and keep watching what happens as you continue. So, when you talk about properties of soil, alright, this is how they behave. So a type of soil will inform you on the management practice you're supposed to do on it. Almost there. What did you record for this?
That's not me.
Who recorded for this? 8 seconds. Who recorded for this?
11 seconds and 14 microseconds.
Pardon?
11 seconds and 14.
11 seconds. This one was 8. Yeah. This was 11. And this one?
1 minute, 36 seconds, 86 microseconds.
Thank you. So that is how these three soils behave. Now, for example, you go and then I ask you now, how do we improve this soil here? How do we improve this soil here? And how do we improve this soil here? The management practices differ on the type of plant you're going to grow, okay? That's why you find in swamps where there are too many clay soils. This is clay, and clay has that ability to hold the water for a long time. It also holds the nutrients for a long time. But the problem with the clay soil, okay? That's why last time I was trying to tell you. That it can have a high okay. So it can hold water for a long time. This is clay, right? This clay. It holds water for a long time. Very good in holding water, right? And also very good in holding what? But the problem is where? I think that. So right now, if you tested the clay soil from here, it will give us a pH which is less than 5, and that is not good for most of the what? The plants. Plants like rice can be grown in the swamp because they tolerate a high, low levels of acidity, and they also tolerate high what? Water content in the what? In the soil. That's why you see people can grow rice in the swamp because they tolerate that too much waterlogging. For them it's okay because they have a high water use efficiency. Then also the pH, they can grow very well in acidic what? In acidic soil, including even sorghum. Alright? So those are the plants you can grow in such a what? In such a soil. Meanwhile, this is soil here which is the sandy loam. Alright? This one which is sandy loam, like the one that we have from around here, this is also very okay. It holds water but doesn't hold for a long time, okay? And it's also not very good because it also lets water what? Very fast. Even this one here is silt loam. Silt loam is very good. It's a characteristic of some of the soils around here. It's good because It holds water but doesn't hold water for a long time. Okay? And you don't need too much water. Are you getting me? And now, when we talk about water, we have three types of water in the what? In the soil. The first type of water is what we call the gravitational water. That's the water that the moment you just poured it here, you saw it coming down, right? That's gravitational water because it just flows as a result of what? Gravitational what? Force. Then now, this is soil. That the gravitational water has gone. What has remained here is what we call the available what? Water. All right. Now this soil is said to be at field capacity. Immediately the gravitational water leaves the soil after raining, after 24 hours, we now have what we call the what? That soil is said to be at field what? At field capacity. Now, when the soil is at field capacity, it has what we call the what? Available what? Available water. Now, this available water is what plants require. They don't need the gravitational water. Meanwhile, for clay soil, it even retains the gravitational water. It has the available water. It even holds what we call the hygroscopic what? Someone getting me right? So, for this soil here, it holds all the three waters at the what? At the same time. So the first water I talked about is the gravitational water that will freely drains because of the gravitational what? Force, okay? Then, after it draining off, the soil is said to be at field capacity and it contains what? Available. And this is what plants what? Require. Then now, when the available water has been taken up by the plants or it has evaporated, now the soil now remains with what we call hygroscopic what? Hygroscopic what? Water. Now the hygroscopic water, the plants will never attract it. How much you fast and pray, you will never extract that soil, that water. Because it is highly attached by the irrigation forces. So you find that if this is your soil, for example, this is your soil complex, and then from here you have different soil particles, right? Of different what? Sizes, right? Now, the gravitational water for it is found at the what? At the larger powers of the what? The soil, okay? And that's why they are able just to flow off because this soil has the larger gaps between the particles, and because I just told you that if you have a sieve which is having very small gaps, and the one which is having larger gaps, if you are to pour here materials, which one will you gather too much at a faster rate under there? This one, isn't it? So even the soil also, because of these larger powers here, the gravitational water easily percolates through and is lost. Now, what remains is what now we call the what? The available water that is attached to the what? And is formed in the small, the micro what? At the micro pores. And that's where the plants are, that's the water that the plants are able to absorb. Then now, after that, around this very soil particle here, there is another thinner layer, small thin film of water, alright? That one there, it's highly attached to the soil particle and the plants don't benefit from that water. So if someone asks you, you're talking about soil water, but which one is available for the plants? Which one is useful to the plant? You say which one? And that one is good when the soil is said to be at what? Okay, so why don't we benefit from the gravitational water? Why? They are linked down to the lower layers, isn't it? So for plants like annual crops and and some other perennial crops that don't have a very deep taproot, they may not be able to benefit from the soil from the gravitational water. Okay? Now, if you have a soil which is, for example, sandy or sandy loam, how do you improve it? Okay? That one there you now bring in the issue of organic matter, right? Organic matter is very important. First of all, one, it is said to be colloidal, or it helps to bind the individual soil particles together, okay? Binds the what? The soil particles. For example, if you have sand soil, you saw its nature, and then you brought in the organic matter, that sticky substance, we call it gelatin, okay? Or chelates. It brings the particles together, and you find that you're going to improve on the structure. And when you improve on the structure, you're going to improve on the water holding capacity. And when you improve on the water holding capacity, you're going to improve on the nutrient holding what? Capacity, okay? And the sum of all that, you also make the sandy soil fertile. Then, the other thing that again organic matter does, you see, when you bring in the organic matter, it has it comes along with the soil organic what? We have the micro living what? Organisms. Then you also have the macro living what? Organisms. So those ones come along with organic matter. Now, those components of soil help very much in soil aggregation. For example, they take in some of the soil particles in them, right, as their food. Then now later, you find that their excreta, or like their fecal matter, comes in but in a very fine what? Particles. No, you guys have all seen this. Who comes from a swamp area? Me, I come from a swamp, I don't deny. Maybe all of you guys, your villages are in town. No. It's okay. You know what we call an earthworm. Yeah. Okay? Now, an earthworm is among the macro, okay? The macro living what? Organisms in the soil. So the earthworm feeds on different materials, including soil itself and soil organic matter. Now, but that process of feeding is called immobilization. They immobilize, like they eat it to support their own systems. Now later, what they bring out as a waste material for us is very good because they help to aggregate the soil and make it finer and even more what? Fertile. All right. Then you also have the microorganisms like the bacteria, the fungi. Those ones also help in a lot of cycles in the soil. They are very important. That's why you cannot deal without what? Without them. And the pH affects the livelihood of what? Those organisms in the soil. That's why you must take care of your pH. The moment you decrease the pH like this, you are affecting their what? Activity. You increase the pH to the extremes, you are affecting their what? Activity. Remember, they are very important in the soil. Any question up to there? Any query? Yes, madam.
I have a little concern about the drainage in this kitchen. This is the same. I expected this one to take a little but I found out that the other
Okay? This one has a larger what? Yes, it's said to be between 0.2 to 2 millimeters diameter, the grains, okay? Then this one here is 0.02 to bring this here, okay? I think that. Then you bring this one here, where you're going to put now, this one is going to be 0.001, 2, then to 0.02. Now, silt loam, this one here, I think that, silt loam, it took how long? 8, okay? How about this one? This is clay. Is it clay loam? And it took how long? Thank you very much. Now, when you have these ones here like this, because for you want the data to take a little bit. You wanted this one to take a shorter, a longer time. Now, I have something here for you. Are you seeing this? This is what? This one, what you're seeing down here, is sand. This is what? This is the silt. And this remaining one here is clay. Clay will never settle. Are you getting it? You have not gotten it. This is called a metric method of determining soil texture. This one you see. This is what? Sand. Because they are heavier, they settle fast. Followed by what? Silt? Silt is not a mix of anything. When you're talking about silt, we have three things that make a soil texture. We define it as a proportion of silt, clay, and sand. So those three make for you a soil complex, which is either going to be silt loam, clay loam, and others. Now, she was asking, why did this one here drop the water later than this one here? Now, it means that this one here, because the level of the concentration of the of clay, or because here, we also have here clay. So, perhaps in this place here, that took a shorter time to release the water. We have not determined how much clay is here. How much clay is incorporated here. Okay? Those are things that what? That's why I wanted us to go through this, but he said this is not very... It would answer you. We may see it like this as sandy loam, but we do not know the amount of clay present in what? In it. Here also, we may look at it as a silt loam, but we do not know how much clay is present there. Are you getting me? That's what brings about these variations here. Unless we go through this, and then we use a soil texture triangle, then you can see, okay, this is 20% clay, 30% silt, and maybe 47% what? But should alter up to what? 100. Can you first bring that? What's the first thing that thing? Okay? This thing is very easy to read, eh? So what I was, we do not know what is the percentage of clay in this what? In this soil. We may say that the thing is perhaps sandy loam or loamy sand here. Eh? Sandy loam here. But we do not know what is the percentage of what? Clay in it. So by the time you have this thing like this, you have it, then you get how many grams are here. Get these grams, divide by the total, multiply by 100, the percentage you get, come and post it here. Someone getting? Okay. This is a method used for determining soil texture. Right? It has the numbers. Okay? So should we read this one first? Yeah. Okay. Use your eyes and observe very well. What is the measurement here for this other soil down?
200 what? 200 milliliters.
Which is the same as a gram, okay? So, for sand is what?
200 grams.
200?
Milliliters.
200 net.
Yeah.
200 and 220. How about silt? The next layer? 260.
460.
460.
Yeah.
460. How about clay? The last one. You have to subtract. Now, this is how you count this thing, okay? From here up to here, we counted it as what? 200 what? 210 or 20. Now, when you're counting, don't you ever shake it, eh? When you're counting the next thing, you start from where you stopped from there. And count only the what? That one. Then also count from here up to here. So tell me the black one. Don't shake, just observe and tell me. The black one is what?
It is 420.
2 what? 240. 5 what? Now, this one here, just add this. Eh? This plus this. Eh? Subtract from the total, you will get this. This is just simple logic. Eh? Add this too. Add this up to here. 460 minus what? 900 what? Don't count the black thing. That's organic matter. That's not soil. Count from that line there. It's what? 1,000. If you subtract, what do you get? 540. Now you get for me the percentage of this. I hope when you add this one here, will take you to 1,000, eh? Yeah. Get for me the percentage of this. So, if we have 1,000 mils, which is the same as here, 1,000 grams, okay? Now get this one here. Get 240 over 1,000 multiplied by 100. What is this? 24. 24? 24? 24%. What do you have from here? 54. This is what? 22. When you add, does it give you 100? Now, what you do with that? Bring now your percentages here. It is helper. We are plotting for, let's start with the sun, which is at the base. Because it settles first, you always count it first. So sun, we said is what? 22%. 22%. Yes. Now you come and read. Please you always read the what? It's what? Are we there? We are counting for sand. Is 20 what? 22, eh? Yes. Now, this is around 22 is around here. Okay? Yes. So you now take 22. Okay? Yes. I'm assuming this is 20 where 22 is. Yes. And then we are taking for silt, which is 24. Silt is here. Yes. It's left. The left line is this one here. Okay? Yes. So it's 20 what? 24. 24 is around here. Are we getting that? Yes. And then how about now silt? You know, sorry, clay? Clay. 50 what? 54. Clay is here. Yes. And 54 is around here. Are you seeing this? Yes. The three lines have met where? Have met here. After plotting that, then you can now read this is soil. That is soil. Is typically what? Are you seeing this? It is clay. Someone has not gotten me. Who has gotten may come and explain to us. Please just come. Okay. We plotted it 22 for sand. 22 is here. Draw a line towards what? Because they are increasing this side. You also take what? This. Okay? Draw this line here. Followed by which one? We counted off silt. Silt was what? 24. So our 24 is around here. We assume our 24 is here. We also do the what? 24. Alright? The last one was what? Clay. The clay content, isn't it? Clay was what? 54 is around here. Draw a line in there, following 54, and then where the three lines intersect, you read it as a soil texture class. And this is our soil texture class here is reading what? Clay. And that's it. So, it means that in that soil there, the clay content is what? 50 what? 54, okay? And then, the sand, the concentration of sand in that soil is what? 22, alright? Then the concentration of silt in that clay, in that soil is what?
24.
So that's what I was telling you. Unless you do this, you can be able to judge now. Yeah, but now you have to. It's okay. You can if you are an expert, even just without using this. Okay, say now, okay, because you must have absorbed, you must have crammed the things now in your head, because you cannot draw all these lines in your head at the same time. So you can plot and you find that okay, maybe the thing is the sandy clay, and sand is what? Yes. Look at this. Are you seeing this? These lines, huh? This red line like this. Follow only the red what? Lines, okay? This one here like this is sandy clay. From here like this is sandy clay long. From here, this alone, this is the sand. You can even just look at the percentage. 100%, this is the sand. Nothing else there. Okay? Yeah. Any question? So you have now come to realize why. That's what I'm going to explain. Anything else? So we've already looked at the drainage, which soil has a high drainage ability, and the faster the water drains, it means that soil is so porous, has large particles, and the more the water drains, it goes with the nutrients. Okay? All right? Yes. Meanwhile, for clay, it drains the water. You also need to drain the nutrients, but the problem is where? The pH, okay? And we looked at how we can improve on the pH of the soil and why. Is there any question? Is there any question? And we also saw different types of soil textures from here, and then how we can improve each of them. Okay? Yes. No. However much you fill it up to here, you can still convert this to 100%. Are you getting me? However much you put it here, you can still convert it to 100. Where is beyond the scale? Which one?
Beyond that scale.
Beyond this one here? This is 1,000. This thing is calculated to 1,000, so you cannot go beyond 1,000 for this calibration. Yes. This ones are not 100. These ones are for 100. Okay? Any question? Any question? Before I ask you, because I'm already asking question before I let you guys go. Let us end with pH testing. Maybe you can come around. I hope you guys have registered. Okay. So this is a standard pH meter. So this is where you read off the things for soil. They always that. That's why I went for a green overcoat, not a white one. So you guys will want to use maximum. Put on this one. Now you have this. This is a pH meter. So this is called the probe or the rod, and it's having a sensor inside it, okay? And this is the screen. This is the on button, calibration button. Then this is also for regulating the pH here, okay? Now this sensor has to be in a distilled water, not mineral water. Mineral water is not distilled water. It's distilled but not deionized. It has to be in a D water. Okay? So that water, you can read from the screen what is happening. It will continue counting until it goes up to 7, because this water is what? Neutral. All right? So, yeah. Now, if you have the water which is neutral, it always has to be inside what? That water which is neutral. So that you can be able to start off reading the pH from here, from neutral to either fall to acidic or fall to what? To alkalinity. All right? Yes. Now, can someone bring for me?
Maybe not. So before I use it to test for whatever soil, I first insert it here until it gets to 7.
You can, but it's still, yeah, that's what it's supposed to be. But you know, someone was keeping on it. It was just in a dry stuff, huh? But it was supposed to be actually in a distilled water, in deionized water, not distilled water. So the sensor has to be in a distilled water so that you read off from 7. But of course, the moment you put it out like this, even the air here is having a different what? pH, okay? And that's why it goes to, because you are constantly here like this, you can see how much carbon dioxide, because remember carbon dioxide will take us to acidity, isn't it?
Yeah.
You can look at how we can affect the what? The pH. Yeah. Maybe it's for me, I don't know. Okay. So it will go up to to that. Then now you have your water. Can someone give me here some? You guys, another class wants to come in. Let's end up with this. Tomorrow we are going to have more introduction.
Now working.
Get me some stick from there. There is some stick down there. 0.1 degrees. So stir it